This video will help to introduce the idea of Bayesian games, which is a new game representation. So here I want to think about auctions. Now, canonically, when we think about auctions, we think about something like this woodcutting from 1885 showing the auction of tea in Melbourne, Australia. We've got a guy in a top hat standing at the front of the room, and he's got a gavel in his hand, and he's probably talking in a funny voice, and at some point he bangs the gavel and somebody just won a bunch of tea. But auctions are a really practical thing. They really are quite important in the world, and they're used for a lot of different things. Here's an example of a much more modern auction. This is an auction of bluefin tuna at a fish market in Tokyo. And you can see this is from 2008. And auctions are used to sell fish because fish spoil quickly and their value changes quickly. And so it's important to find a way of determining what the prices should be on a day-by-day basis. Here's an auction by the US Marshal Service selling some horses that were seized by somebody who was convicted of embezzling money. And so the US Marshals got a bunch of guys in cowboy hats to round up this person's horses and sell them off to recover some of the embezzled money. Again, you can see why an auction might be used here, because the value of something like a horse is pretty unclear. It depends on supply and demand. It depends on intangible things like the value of the horse, the number of other good horses on the market at a given time, and so on. Here's yet another auction. This is an auction of rugby players, presumably only for a limited time. And again, you can see why an auction might need to be used, because it's pretty unclear what this guy would be worth. Of course, not all auctions happen in person. Here's a famous auction that occurred on eBay a few years ago. This was a situation where a woman in Florida was eating a grilled cheese sandwich that she had made for herself. You can see a picture of it right here. And she took a bite out of it, and then she was amazed to discover what she considered to be a perfect likeness of the Virgin Mary in the shape of the burn mark on the grilled cheese sandwich right there. And so she was so amazed, she decided that this was a religious relic. She stopped eating the sandwich, and like anyone would do if they discovered a sign from God, she posted it on eBay to sell to the highest bidder. This is kind of interesting, both because it's ridiculous, but also because it goes to show how the internet allows auctions to create markets in places where they really wouldn't have existed before. So if this had happened before the internet, it seems pretty clear that this woman would have had a hard time finding a buyer for her grilled cheese sandwich. But you can see that when I took this screenshot, the auction still had almost 4 days to go, and already the top bid was $7,600 US. And this really was not a hoax. This was an actual auction. It was covered in the news. So that's kind of an amazing thing. It goes to show the power of auctions to match up buyers and sellers. Here's the last auction picture I want to show you. This is what's called a silent auction in a charity auction. So what's going on here is there are actually two different bundles for sale. So there's a gift basket here for sale, and all of the people who are interested in buying it are able to go up and inspect it, decide what they think it's worth to them, and then they write a bid. They write their name and an amount that they're willing to pay on this sheet of paper here. And the reason that I think the silent auction is particularly interesting is we can really see how this might look like a game. We here have a well-defined action space. You come, you look at the piece of paper, you can see the moves of the players who have moved before you, and then you take an action, which is choosing to write down a number. And at the end, presumably, you don't write down a number that is worth more than the gift basket is worth to you. At the end, if you have the highest number, you win the gift basket. You realize an amount of utility, which depends on how good the gift basket is from your point of view. And you pay whatever amount it is that you wrote down on the piece of paper, which is presumably less, and you get the difference as your utility for having played the game. So all of this looks like something we can really model in the context of this course, And if we realize we can model the silent auction this way, we can probably see that we can model the other auctions that I've just described in this sort of way as well. However, there's something really critical about the case of the silent auction, which is different from the games that we've talked about in this course already. And that is that when I want to reason about what other people will do in this game, I need to think about what they think the gift basket is worth to them. That's going to be something very important to the way they choose to act in the game. And critically, this is something that will affect their utility, and it's not something that I know. And so this is a case where I'm not quite sure what other players' utility functions are, even in cases where I can imagine what all of the actions taken in the game are. So this is a different sort of setting than we've ever looked at before, and hopefully you can see that this is really necessary to model the case of auctions. It's really fundamental to an auction that I'm not quite sure what the good is worth to all of the other participants in the auction. And that fact is really critical to my strategic reasoning in the auction. So Bayesian games are a formalism that allows us to model this kind of uncertainty about the utility functions. And this week we'll go into Bayesian games in more detail. It turns out there are several different ways to define Bayesian games. This video is going to give the first definition. So before thinking about Bayesian games, everything we've thought about has assumed that all of the players know what game is being played. That is, everybody knows how many players there are in the world, what actions are available to every player, and what payoffs would result given a complete action profile or an action vector by everybody. So let me give you a chance to stop and think about why this is still true in imperfect information games, because intuitively it might seem to you like it isn't true. So you might want to pause the video now and think about that, and then I'll tell you the answer. So the reason why imperfect information games still have all of these things being true is that what you don't remember in an imperfect information game is what actions other players have played at the moment when you're about to take your own action. But it's still the case that you know what actions are available to everybody, and it's still the case that if you know what everybody fully did, a complete action profile by everybody, what payoff would result. Now we want to think about games where these assumptions aren't true anymore. So well, we are still going to make some new assumptions, so let me tell you about that. So what we're relaxing is that all players know what game is being played. So we're now going to think about the idea that there's more than one possible game that the players can think about. And among all of these possible games that the players will reason about, they're all going to be games that have the same number of agents and the same strategy space for each agent. So how they're going to be different is just in the utility functions. And that's important because it's just difficult to model a situation where you're not quite sure what strategy space you have. It wouldn't be clear how to act. Now, you might find it useful to reason about games in which you're not sure what other agents there are. It turns out that's actually possible to capture within this framework. In that case, you would just always believe that the maximum number of agents were present in every game, but you'd set up the utility functions in a way where sometimes it doesn't matter that some of the agents are present because they're not able to affect anything. The second assumption that we're going to make, it has to do with the beliefs that agents have about these different possible games. So in order for this to work, it has to be the case that agents still have well-defined beliefs about what is possible in the world. And we're going to say that the agents start out with a common prior. So that is, everyone has the same beliefs about what it is that's possible in the world, what games it is that are possible. And then they might get individual private information about, in fact, what game is being played, and then they'll do Bayesian updating. So they'll end up with a posterior belief which is obtained by starting from this common prior and updating it based on their private information. So that's an assumption. We could believe that the agents had different prior beliefs, but that's not what we assume in the case of Bayesian games. So here's one definition of Bayesian games in terms of information sets. So a Bayesian game is a set of games that differ only in their payoffs, also a common prior defined over these games, and a partition structure over the games for each agent. So, in other words, a Bayesian game is defined by 4 elements. The first is a set of agents. The second is a set of games. Recall that a game is defined as a set of agents, a set of action a set of action sets, one for each agent, and a set of utility functions, one for each agent. So we're going to restrict this set of games here to all have in common the same set of agents and also the same action sets. So these games are going to differ only in their utility functions. Then P is going to be an element of the set of all possible probability distributions over games. This is going to be our prior distribution. So this is going to tell us how likely each of these games from the set G is. And finally, we're going to have a set of partitions of G, one for each agent. So this is going to be a set of equivalence classes that will say, from the point of view of an agent, certain games are indistinguishable from each other and others are not. Let's look at an example. So this example is a little bit contrived. Ordinarily, we're going to use Bayesian games to model something that kind of makes some sort of sense in the world. And here, really, we're looking at something kind of artificial. But it's a small example that still lets us think about everything important about a Bayesian game. So the first thing to notice is that there are 4 possible games that might be played: matching pennies, prisoner's dilemma, coordination, or battle of the sexes. Incidentally, prisoner's dilemma here is being played with different payoffs than you might have seen before, but that doesn't matter. It's strategically the same game. And we have a common prior over the games. So there's a 30% chance that the game that the players will in fact be playing is matching pennies. There's a 10% chance that they will in fact be playing prisoner's dilemma, 20% chance of coordination, and a 40% chance of battle of the sexes. Now, I haven't marked the actions in these games, but our assumption is that they have to be the same. So let's say player 1 has 2 choices, top or bottom. He gets to choose the top or bottom action, and it's the same in every game. And likewise, player 2 can choose left or right, and he gets the left or right action in each game. So what is interesting here, of course, is that we have these information sets. So player 1 gets to find out which of these 2 sets the game is in. What that means is, in fact, nature is going to decide which game gets played. So randomly, it's going to be decided which of the 4 games being played according to the common prior. Let's say the most likely thing happens, and the players end up playing Battle of the Sexes. In that case, what player 1 is going to find out is that he's in this equivalence class rather than this one. So that means he's going to know for sure that he's not playing matching pennies or prisoner's dilemma, but he's going to think that he might be playing either coordination or battle of the sexes. He's going to have no way of telling them apart. Now, player 2 has different equivalence classes. So player 2 considers these 2 games to be indistinguishable, and likewise considers these 2 games to be indistinguishable. And continuing our example from before, if this was really the game that was randomly chosen by nature, then player 2 would find out that he was in this equivalence class rather than this one, meaning that he would think the game being played was either Prisoner's Dilemma or Battle of the Sexes. And the ground truth would be that, in fact, Battle of the Sexes was being played. He would consider it possible the Prisoner's Dilemma was being played, and we've already seen that player 1 would consider it possible the coordination was being played. And what this means is that when the players are deciding what action to take, they're going to have to play an action without fully knowing what game is going to be played. And they're going to have to reason about what their opponent is doing without fully knowing what the opponent is going to think. They do know everything about this setting. So this whole kind of picture is something that the players know. they know the common prior, they know their own equivalence classes, and they know their opponent's equivalence classes. So if I'm player 1 and I want to reason about what player 2 is going to do, and I know that I'm in this equivalence class, then I also know that player 2, that if the game is really coordination, which I believe is possible, then player 2 thinks he's in this equivalence class and thinks that matching pennies is possible, even though I know it's not possible. Or, on the other hand, if Battle of the Sexes is the real game that's being played, then I know that player 2 thinks he's in this equivalence class, which means he's going to think Prisoner's Dilemma is possible, even though I know it's not possible. And I'll leave for a future video actually how we reason about these games, but what we've learned here is how to define a Bayesian game by writing it as a probability distribution, a common probability distribution over multiple different normal form games, all of which share the same number of players and the same action sets.
So here is an alternative definition of Bayesian games that is essentially identical mathematically, but presented differently. It's based on types, or more fully epistemic types. And the type of the agent is supposed to capture everything that's private information to the agent. So if you look at the first definition of Bayesian game that we saw having to do with uncertainty about types and the common prior, then the type of the agent was her private signal, that is the information set in which the chosen game lies, as well as everything that emanates from it, namely her beliefs about what the possible information of the other agents are and information of the other agents about herself and so forth. So all of that is folded into the notion of a type. So that's mathematically very convenient, packing all this information into a type. Formally speaking, then, the Bayesian game is defined as follows. It's defined as this tuple that is as follows. We have a set of agents. We have the actions available to the agent. So now we don't have sets of games. We have very directly the actions available to the agent. And now we have the type, this abstract mathematical object that captures the private information of the agents. So we have a type for each agent. And we have a common prior. As in the first definition of games, we have a common prior, but now it's not over games, it's over types. So each agent has the type, and that prior is common. The type is chosen according to a probability distribution that's commonly known by all the agents, and each agent knows their own type. Therefore, they also have a posterior about the type of the other agents and beliefs about what the other agents might believe about their own type, and so on and so forth. This is the type of the agent, and we have the utility function now depend not only on the actions taken by the agents, but of their type. That's the formal definition. Again, it's mathematically, in some sense, very simple, but the intuition is complicated because the notion of a type packs into it a lot of things. So let's see it in action. Consider this game that we saw when we discussed the first definition of Bayesian games. Again, we had 4 possible games being played, chosen at random by nature according to this prior, and we had the private signals, the information sets that the agents found themselves in. Here is the type perspective on this. So what are the actions available to agents? Very simply, the row agent has the up or down actions, and the column agents have the left or right actions. The payoff, however, will depend on their type. So let's look, for example, what happened here. So what is the payoff when the row agent plays up and the column player plays left? Well, that depends. If the type of the agents is this one, well, what is the type? The type corresponds now to this information that they have. And the type of the second player is this. Well, what's the path then? Well, the path corresponds now to this cell right there, is what happens when they play up and left. And so you get 2 and 0 when the types are as they are. Let's take some other random example here. Let's clear the slide. Let's take some other example here, clearing the slide. And let us look, for example, at down and left when the types are these. Well, what is the types? So the type is this one right here. So this is the information available to the first agent. The second agent has this information available to her, which means that this right here is the game being played. And what is DL? DL means that we're playing down and left, so it would be this one. And therefore the payoffs will be correspondingly 0 and 0. So you can look at other examples and figure out what the type-based formulation means by just taking some random row here and figuring out why the row is the way it is. The last thing to say here before we move on to analysis is that in this particular example, by fixing the type, you ended up with a very specific game. And this is a complicated topic where, in fact, if you wanted to map it to uncertainty over games, you may not have a unique game, and you need to look at the set of games and the expectation there. But I'm just flagging this as a topic. What we discuss will give you a good handle on the two formulations of Bayesian games: the explicit listing of games and a common prior over them, and a partition structure for the agents, or the type-based formulation.